Hi there, and welcome to our lecture on energy transfer. This is Heat 2 of Unit 8. Our key ideas: how does energy transfer happen? What do conductors and insulators do? And what makes something a good conductor of heat? Alright, so our first question, basically we're looking at methods of energy transfer. So heat energy can be transferred in three ways. These are conduction, convection, and radiation. So we're going to look at each of these in turn. Conduction occurs between two objects that are in direct contact. And if we look specifically at thermal conduction, it's the transfer of energy as heat through a material. So in order for conduction to take place, some object or material has to be in contact with another object, typically a hotter object in contact with a cooler object. Convection is going to result from the movement of warm fluids. So convection is the movement of matter due to differences in density caused by temperature variations. Convection can actually occur in air or a liquid. So remember that fluids is a general term that describes both air or gases as well as liquids. So if there's differences in density because of temperature differences, that convection is going to take place from the warmer air to the cooler air. So it'll end up transferring that way. When that happens, what we can get is something called a convection current, and this is the movement of matter that results from different densities. And these currents may move vertically, or maybe they move circular or cyclical, which is also a circular pattern. And whenever we heat our house or cool with a heater or air conditioner, if it's being forced through the heat register, then it's going to involve these convection currents. So looking at conduction versus convection, so before conduction can take place, the average kinetic energy of particles are the same throughout, so we've got the same kinetic energy. And then as conduction takes place, so if we heat one side of, say, a metal bar, the heat is going to transfer. So these particles are going to heat up and move faster and cause this thermal energy, this kinetic energy, to be transferred through this object. Whereas with convection, say we've got this heat source again, it's obviously going to warm the air directly above it the most. So what happens is it's going to move upward, and as it hits the cooler air, it'll gradually come back around. And basically what's going to happen is this warm air rises, and this cold air, this current or this cycle that takes place. Alright, so radiation is the other form of energy transfer. It does not require physical contact between the objects. So radiation is the energy that is transferred as electromagnetic waves. So this comes to us such as visible light and infrared waves. And we'll talk more about electromagnetic waves in the next section. All objects are going to give off some kind of infrared radiation. So we are actually emitting heat, but it doesn't fall in the visible spectrum, it falls infrared. So it's not something that we can actually see. We actually have to have an infrared camera to detect the heat that we're radiating. So unlike conduction and convection, radiation does not involve the movement of matter across space, so we don't need to have actually anything between here and there. One of the most common examples of radiation is from the sun. It can travel through the vastness of space and still heat us up, so it doesn't have to have gravity, or it can be in a vacuum, basically. The other two forms of energy transfer cannot travel through a vacuum, so they don't actually travel in space, or can't be transferred in space. And again, most of the energy we receive from the sun is transferred through radiation. Alright, conductors and insulators. What do conductors and insulators do? A conductor is a material that energy can be easily transferred as heat, and then an insulator is a material that transfers energy poorly. So we can see this easily whenever we cook. if we have a pan that's got metal handles, well, those handles get very hot when the pan heats up. But then if we've got another pan that's got a wooden handle, then the wooden handle is safe to touch because that wooden handle would be an insulator. It doesn't transfer energy very well. So heat energy is transferred through particle collisions. So as particles collide, this energy is transferred. Gases are poor heat conductors because the particles are spread out, they're far apart, they're moving quick anyway. So denser materials usually conduct energy better than less dense materials do, such as metals that tend to conduct better, whereas plastics don't conduct very well. Alright, we've got something called specific heat, and the question here, what makes something a good conductor of heat? So what makes a substance a good or poor conductor depends on how much energy is required for a change in temperature of the substance by a certain amount. And we've got a value called specific heat. This is the quantity of heat required to raise a unit of mass of material. We're going to call it a homogeneous material, or homogeneous. So it's all the same throughout. So it's just water, or maybe just salt or something. So let's just say the water. So we're raising 1 Kelvin or 1 degree Celsius in a specified way given a constant pressure and volume. Alright, so specific heat is going to describe how much energy is required to raise an object's temperature. And this is a physical property. We can do it without changing the substance. We tend to represent specific heat with a lowercase c. And we can use it to figure out how much energy it takes to raise an object's temperature. So we can use the equation energy is equal to specific heat times the mass of the object times the temperature change, or energy is equal to lowercase c times lowercase m, and then we use this delta symbol, delta T, just change in temperature. So delta again is showing us change. Alright, so here on this slide we've got some values of specific heat. So we can see water here has a value of 4,186 joules per kilogram times Kelvin. So this is the specific heat of water. So we've got several other values here. So you can see the water's got a very high specific heat. So it's very, it doesn't like to change its temperature as well as some of these with lower specific heat. So it doesn't take as much to heat up that iron that's in that pot that we're cooking on the stove compared to the water that's actually in it. So that's why it takes a while for water to get to a boil when we're trying to heat it up. Alright, so looking at a specific heat calculation, so how much energy must be transferred as heat to 200 kilograms of water in a bathtub to raise the water's temperature from 25 degrees Celsius to 37 degrees Celsius. We're going to list what we know. So we're given the change in temperature, 37 degrees Celsius minus 25, which is a 12 degree Celsius change. So our change in Kelvin is 12 K. So it's just the degree differences between these. So instead of converting these to Kelvin first, the difference between these is 12. So we can basically transfer it from 12 degrees Celsius. So our change in temperature is 12 K. Our mass is 200 kilograms. Specific heat from our table is 4,186. Alright, so we want to find energy. So we're going to use the equation energy equals Cm delta T. Plug in our values. So the 4,186 joules is our C with 200 kilograms, and then our change in temperature is 12 Kelvin. So kilograms cancel, Kelvin cancels, we're left with joules. So we end up with 10 million joules, or we can convert this to 1.0 times 10 to the 4th kilojoules, or 10,000 kilojoules. So heat raises an object's temperature or change the object's state. So while a substance is melting or boiling, the temperature does not change. So we've got our ice cube, and as time progresses and temperature is increasing, we're adding energy, and we get to a melting point, and then we continue adding energy, we get to a boiling point, so the temperature continues to rise as energy is added. Thanks for listening.